Ladies and gentlemen, please welcome Mr. Guiseppe.
As the subtitle of this event was Can Machine Think? I wanted to analyze the problem of thinking by creating something which is a presentation which is probably not very mainstream. And the main concept is understanding the difference between human minds versus artificial intelligence. And I don't want to take too much time in the introduction, so I want to just start with a warm-up. And I want to ask you, what does expression mean, of course, for a non-mathematician? This expression is quite simple. Probably most of you know it. There is a number, a fraction, a power, another number, a letter on the other side, okay, a symbol, limb, but there is also this other thing here, which is very scary for the majority of people, because this thing is the difference between what we consider limited by to some extent, and in fact, for any computer, actual or potential, we can transform the expression in a sort of another expression that we can call approximation of E. And this is a long number with a certain number of digits. We can increase n, we can have a zillion digits and get at a certain point an overflow. It's impossible to have any other result. We can create the largest computer in the world, but this number will be always limited. For a human being, the situation is completely different. It's different because of these three dots, and we are going to discuss about these three dots here. This is a simple difference that makes the real difference between minds and what is not mind, because we know that this number E is a particular kind of number, and we are going to discuss about this. But this number has an infinite number of digits, and there is no periodicity. And we can use the expression infinite, in this case, infinity, and we can say that when we reach infinity, it doesn't matter if it happens or not. This number has full dignity to be a number, not just approximation. So the start and ending point of this presentation can be summarized in a question. Why can we easily manage infinity and undecidability? Infinity in the sense that we want to answer the question if 1 plus 2 plus 3 plus whatever can really continue forever, or undecidability if we have a proposition that can be either true or false, and we have no ability to answer this question, not because we don't have means, but because it's impossible to decide whether it's true or false. So let's start with counting, first of all, which is the easiest thing that everybody knows. We have 3 apples, and we decide to draw 3 lines on the wall. We can put each apple in correspondence with each line, and so we get what we can call a correspondence. We don't care about the named numbers in this case. I'm using the real numbers, actual numbers, but we can just say one line, forth. It doesn't matter. There is a correspondence. So there is an abstraction between 3 apples that can be also 3 stones, 3 horses, 3 whatever, and 3 lines. This correspondence creates this abstraction we can call number 3. And the first question that we want to ask and want to answer is how many elements does this set that we have defined, which is the set of the numbers 1, 2, 3, so forth, natural numbers, contain? Very trivial for everybody, but there's a problem. We start considering that we have an element. Well, we know that there is a simple recursive loop. We have a generic element n that belongs to the set. So if we define that, we are not going to do it now, but we define an operation called addition, n plus 1 belongs to n. But in reality, what we do is taking our n's, for example, and start counting. Again, it doesn't matter if we count 1, 2, 3, 4, 5, but you can say dot, 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 dot. You can repeat the same word any number of times. And at a certain point, we ask the question, where is the end of this sequence? So the real problem is that it's necessary a mental shift or an additional abstraction to step from a finite or any finite representation to something different that is not finite. And this something different is obtained thanks to the usage of an extraordinary scope. This shift is called language. And we can define language as the most powerful invention made by human beings. It's probably the most important thing that being discovered that together with other elements will make the difference between humans and other animal. Just to confirm what I'm saying, I put a sentence from Wittgenstein. First, Wittgenstein, in his first period of his life, he studied language, and he wrote in his Tractatus, the limits of my language means the limits of my word. You can also read this way. In other words, whatever you can describe using language is real to some extent. It's something that is in your word. Whatever is describable, it's conceivable by language as a certain degree of reality. And of course, it's necessary here to continue reading Wittgenstein to understand when these possibilities are really true. And we will shortly discover that it's necessary to introduce another element to avoid a problem. But let's, for a second, restart with the problem of counting by considering a poor guy here. Imagine a guy 100,000 years ago in his cave that decided to carry out this task. So it says 1 belongs to this set. The other number 2, I take 2 apples. Then I have another apple, get 3 apples. And he said, I can continue this process, but one day, no, I will die. So how can I solve it? Well, I can simply do this. After my death, before my death, of course, my child can know the last number that I call N1, where I stopped, and she can continue. And she can continue repeating this procedure with a child and so on. This is clearly a pure abstraction that we can do thanks to the interaction of language. So even if when I say I is the guy here, I never reach the end of this process. I know that there is some sort of limit. Pay attention, limit, not number. A limit is a sort of entity that is greater than any number I can imagine. But it's a sort of whole, say, everything. And this guy is here. It's a symbol, infinite, that says, here I am, here in your mind, hidden in your mind. You can conceive me, you cannot arrive to me because I have not the consistency of a number, but here I am. Let's now, 1 second, focus on the process of putting together these 3 elements. I told you before, language alone has some problems. I will show you immediately. We have to put together language plus logic plus science to get mind. And to show you this, I will produce these steps. We start from real world, where the ground is, where at this point we have a perception through our body. We use our brain to perform internal representations. And then we enter into a world where there are 2 elements that they are both partially modeled by artificial intelligence. And the first one is abstract elaboration, but lower level. And this abstract elaboration is always grounded through logic. Grounded means that whatever I elaborate, whatever I think, must return to some extent real world. I cannot invent. I cannot just say whatever I want. And it's also the way we can sum n numbers, for example. So something that we can count using a finite procedure. But there is also another step that I define as transcendent elaboration, which is a higher level grounding also. But this higher level is something that drives us to understand that there is something beyond. And this something beyond is extremely interesting. I will show you some examples which are really stunning. So, 1 second, return to the concept of language. And first of all, let's see if language can create reality alone. Well, think about this tree and this lion, and think about these three statements. The tree is on the left, the lion is on the right, it's perfectly correct. The lion can walk away from the tree, perfectly correct. The tree will hit the lion, perfectly correct. Yes, using only language, that's perfectly correct. There's nothing wrong in this, use only language. But we know that a tree cannot hit a lion. We have to introduce another element, which is logic. Logic can create contradictions. So we can say the tree cannot move, the lion can, correct? But trees can eat a lion, it's correct. I think trees that can eat a lion, or all lions can run away. Well, this is false, because maybe a lion can be dead or can be paralyzed. So it's not correct. There is another contradiction. Logic performs the grounding, so allows to create abstractions by performing grounding. Now let's see how we can use these three elements all together to perform abstractions, which are more and more complex. So to perform internal representations, to work with internal representations and obtain real abstractions. So starting from the first, an adult lion is average too heavy to stay on the branch of a tree. Fine, correct. Another body with the same mass of an adult lion will break the branch of the tree. Well, this is another statement where there is an abstraction, there is another body, whatever it is, and I put mass. I understand that the lion itself is not important, it's the mass will break, in this case, branch of the tree. But I can perform another abstraction using a little bit of more imagination based on always on the grounding that confirms what I'm saying. And I say it's reasonable to imagine the existence of a tree whose branches can hold a lion. Well, it's true. Yeah, of course. I can imagine that a branch is so resistant to hold a lion, or the lion is so small to stay on the branch. It doesn't matter, but it's correct. So we have this pyramid here, or a tower, whatever you want to call it. And it's a sort of infinite tower of abstractions. We start with the perceptions and the reactions. This is the word of animals in general. Not animals in general, perceptions and reactions, perceptions. But we have to introduce the language threshold, and the language threshold define the boundary between the world of pure animals and the world of human beings. We have the first level of abstractions where any statement can be true, and this is what we have discussed before. Then we introduce another threshold, which is the logic threshold, and here we have the logic reasoning that allows for statements which are true. When I say logic, I'm not referring to Aristotelian necessarily. We can think about more complex logical procedures, we can think about probabilities. However, we can think about all the developments of logic. And then have another abstraction. I put hand very can be subsequent, but it can be after some levels where there is creativity, transcendence, and whatever else. And by the way, the cow that is depicted here is in a cave in France called Lascaux, where about 17,000 years ago, human beings were depicting on the cave 17,000 years ago, not just yesterday, and they were already doing this. So let's now return 1 second set of numbers again, and let's think about half a apple. We have also half apple. We know that it's quite easy to represent half a apple using fractions. I'm not explaining this, it's obvious, but there is a question that is natural, is how many fractions are there between 1 and 2? Again, please don't think that you as a human are trying to understand this, but think also about machines trying to understand this. And well, in this case, it's easy to see that there is a crowd of rational numbers between 1 and 2, and well, they are infinite. I can just increment the denominator of each fraction to have easily an infinite number of rational numbers between just two natural numbers. So we can rephrase the problem and we can ask something that is here is not defined in pure mathematical terms. So please understand that this is not extremely rigorous, but the concept is same. And we want to know the infinity of Q. So the number of elements of Q is the same as the number of elements of N. We have just seen that in between two numbers of N, there are infinite numbers of Q. So infinite rational numbers. So intuitively, we say, well, no, it's impossible to be much larger. Well, there's a proof, clever trick called diagonal proof. I'm not explaining this, of course. It's a pure abstraction based on the idea of infinity, but it's very interesting and you can prove if you write the fractions using this approach and move diagonally, you can create correspondence between N and Q. So N and Q have the same size. This is something that requires a very high level of abstraction to be discovered, but they have the same size. Well, now let's call another guy, Pythagoras here. Pythagoras was very, very nice. He discovered a theorem that everybody knows, and we have a square with the sides equal to 1, and you know the diagonal is square root of 2. Well, immediately everybody knows square root of 2 is a rational number. Well, proof, I'm not discussing this, no time, but it's very easy to discover that square root of 2 is not rational. Square root of 2 doesn't belong to Q. And believe me, for that period, this was the worst earthquake happened in the Greek culture. The Greek culture saw in natural rational numbers the perfection. So the idea of the existence of these numbers was considered as worse as something as heretic. So something that was completely unacceptable. Rational numbers are not alone. We have to define irrational numbers, and square root of 2 is irrational, whatever it means, that doesn't matter. But after a while, somebody tried to create this new set called real numbers. And this set is the union between the rational, the fractions, and all these numbers feature the numbers with an infinite number of digits without periodicity, so they cannot be represented as fractions. Here in this line, I put just 3 examples: square root of 2, e, and pi, which are extremely famous. And of course, at this point, we can ask the same question as before, and we want to check the ability of our brain, but we say we have learned the lesson. So as n and q have the same size in terms of infinity, r should be the same. Well, it's obvious. Unfortunately, no. A guy called Georg Cantor arrived one day and discovered r is much, much larger than n and q, and find the difference between n and q, which are called countable. In other words, they can be put in correspondence with natural numbers. You can use your hand 1, 2, 3, 5 for n and q, and r which has an external power, something which is not contained in the first set, and this power is called power of continuity, and R is called continuous and is also discovered. Hypothesized, discovered. This is not proved yet, that there are no other infinities between the infinity of amplitude and the infinity of R. Clearly, I'm omitting kind of proof, but this guy, it's not difficult to prove this. Understood and proved that R is much larger. So the infinite R is much larger. Okay, I have to jump, but we will return to this. All this discussion was to create the first part of the discussion, but we have to wake up another guy, Turing. It is here, probably was a teenager here, and we want to use this concept of Turing machine. And I think that everybody has clear the concept of Turing machine, but just sure, we can consider a Turing machine as the union between a computer, sort of computer, and a program. So a sort of machine that can receive a program and as a deterministic CPU and an infinite tape where to write the results. So let's say this. I want to create a Turing machine that can always decide whether the input program that we call pi, and T1 of pi is a very simplified representation of the Turing machine, and can write either true or false if the program stops or not. It's very easy, you know, when if you are a Python programmer or Java, C, whatever, you know, while true, do this, and this is clearly an infinite loop. Program never halts. Instead, if you do I 1 to 10, the program halts. Very easy, obviously. So we have this Turing machine here, gets the input program, performs its elaboration, and then decides, yes, the program halts, true. No, the program doesn't halt, and right, false. At this point, let's create another Turing machine by wrapping this machine into another one. It's very easy. We take the first one, we put the first one inside another machine that's called G2, but after writing true, and remember, T1 can always decide whether the program halts or not. So in this case, after writing true, we create true, and after writing false instead, so in this case the program never halts, we create stop. We can hand the program, we can put a return. At this point, we can, this trick, we can just plug T2 into T2. So we can say as T1, which is the core of T2, can always decide, T2 should be able to decide whether it stops or not. But here everything breaks. Because when T2 writes true, T2 loops forever, you remember? And when T2 writes false instead, so in this case should loop forever, T2 halts. In this case, problem is undecidable. In other words, it's impossible to know whether a program will halt or not. Or in other words, there will always a program that is undecidable. Not in every case, but there always is a program that is undecidable. So if we return to our tower and we start from the bottom, we know that T2 cannot solve the halting problem. Okay, don't worry, we can simply create an exception and we create T3 and we include this exception for T2 just to solve the problem. Everything is fine. No, T3 cannot solve the halting problem again. Okay, we create another exception, but we continue forever. And there is always the undecidable problem there waiting for us. But this guy here on top of the tower says, well, I can create all the examples. I'm always on top of this problem. Wherever you believe it, I can always create an example. So I'm much more intelligent than what you think. But there is something interesting that happened at this point. And this summarized in this church-Turing thesis. I will show you 3 examples of this thesis. Pay attention, these are not theses. These are hypotheses. In some cases, it happens that a thesis, a hypothesis, the thesis, but they are called in this way. Church is Alonzo Church is a mathematician that created lambda calculus, and the first one says any deterministic computer device is representable either through Turing machine or lambda calculus. Any deterministic computer device. Okay, this one is quite simple to understand. And let's say that no one has right now said, well, this is really wrong. There's a problem with this version. This version says it's not physical and say any deterministic procedure computable in finite time by any physical device is also computable by a Turing machine. Attention, any procedure computable finite time by any physical device means also our brain, is also computable by a Turing machine. There are many other versions. Another one is a little bit stronger, it's strong, and says that the difference is that instead of finite time, in this case, there is polynomial time. This one is threatened by quantum computing, but we are not interested in this one because the real problem lies in the second answer. Because in the second one, we arrive to the starting point again. We have analyzed all the problems of infinity, what the brain succeeded to do. And the question is a human brain or a mind, to be more precise, a Turing machine? And if not, what kind of computing device? This is the question. And this is a question that I will ask to you all, to the aspiring data scientists, to the new data scientists, young, the old, whoever. This is the future of AI. If you can answer this question, you can really create a jump in AI. So thank you very much.